Welcome. Alright, don't hire a hitman. This isn't my fault. I know you're looking at a ton of meters here, but we can thank the idiots that are into square wave compression that has led us to this. However, to be really honest, I'm actually damn happy we've got to this stage because we should have always used true peak meters. However, because we had the migration over from broadcasting into audio production, things had to change. Now, this first video, which is one of a series of 3, will concentrate on what a meter is, how it works, and how we read it. We'll also cover the basics of calibrating the meters to display the same information. I mean, there's no point having one VE reading and one ppm reading that are not calibrated together. Now, that way we can, restructure our meters to display only the information we want. So let's start with the most basic of all meters. I'll leave this here actually. We'll get rid of that. We'll work on these two for now. And I'll leave these here because I'll be constantly referencing to ppm meters as well. So let's put this into master mode. Take the scale out. So we're only dealing with digital full scale. Right. Now the VU meter, believe it or not, was developed before the ppm meter. The ppm meter is what most DAWs have. In fact, all of them do. They're called program peak meters or sample peak meters. And basically they reference and display the audio decibels full scale. Let me explain what that means. The full scale is, in a digital domain, is the entire range of your meter. On some meters, they'll go up to 96. I don't think we need that much extension. This one's 48. So what we're really concentrating on is the area around 0. When you have unity, which is the best signal to noise ratio at input, what we want to be able to do is to have that unity floating around 0. This is why we keep all our faders at 0. The idea is to use this fader as a fine-tuning mechanism as opposed to just moving it down a little bit and suddenly you got like a 10 dB jump. We don't want that. We want to be able to extend this fader as much as we like and only move over a few dBs. Now, the VU meter, and you're probably not going to believe this, but it's actually the truth, was developed in 1939, or rather it was released in 1939. But here's the deal, the ppm meter was actually developed in 1932 and released a year before the VU meter. Now the VU meter, and VU stands for voltage units, only shows an average signal level. It doesn't give us an accurate indication of perceived loudness, which is what we're after. However, what I do like about VU meters is that the way they represent the values is pretty much how our hearing behaves, i.e. logarithmic and average. Typical sample peak meters, or ppm meters as we call them, they show the highest amplitude sample in a group of samples. What they don't measure is intersample peaks, and there's a reason for that. It's all about the integration rate of all these meters, and we'll come on to that in a minute. Because these are program peak meters or sample peak meters, people often think that they're true peak meters. They're not. To distinguish between the two, we call ppm meters quasi-peak meters because they're kind of fake peak meters. Although they give us the information we need in terms of a group of samples and picking the highest sample amplitude value, they don't give us the kind of information we have in terms of perceived loudness. Think of the VU as just an averaging voltmeter. However, what I do like about some of the VU meters we have nowadays is that we also have ppm. We don't have to use it in VU mode. We can actually work in ppm, and we can also set standards. We'll come to that later. So how do we test these VU meters? How do we calibrate them? How do we get them going? Well, we run a sine wave through them, and I'm going to do that now because I want to show you something that's actually very, very important. And that's distinction between RMS and peak. RMS means root mean square. It's an average value, whereas peak is peak. how do we work out the RMS value of anything? For example, you have peak normalization and RMS normalization. If you need to know that, go and watch my video on normalization. I explain root mean square and have audio examples and screen captures before and after, so you can actually see how an RMS structure affects the audio. If we run this sine wave, and I use this, it's a free utility from MDA. It's just a test tone generator. We use it for testing equipment and calibrating meters and all sorts of things. Get this damn thing because it has sine, pink noise, white noise, logarithmic, it sweeps, it does all manner of things that you can use. Get it, it's free. Right, let's generate this sine wave. I've put the mode on sine and I've selected 0 dB because we're working in 0 dB full scale. Think of full scale as the range of the meter with the ceiling set at 0. In the digital domain, when we're dealing with decibels and numbers, you cannot exceed 0. Value here is 0, 0, 0, 0. Let me show you what happens here. On the ppm, I'm also getting a value of 0. On the VU, I'm getting a value of 0. We can change all of that behavior, which we'll come to later. For now, let's just calibrate these things so that they read the same. 0. All the references and all the standards have been set to 0. So we're working in 0 dBFS, which is digital full scale. When you look at this test tone and when we're generating a sine wave, you'll see that we have an average value here of -3 dB. This is the RMS value across this channel using ppm. If we're calibrating to 0 like I've done here with both meters, again very easy to do, we need to do the same here so that our RMS and peak are calibrated to 0. To do that, and because we're in digital scale, i.e. we're using dBFS here, we need to switch on the AES 17 recommendation. When I hover over this, you'll see it says in brackets +3 dB. This is the compensation for RMS to peak. When I click this, I've now calibrated back down to 0. Perfect. Let me switch that off for a second. Now let's talk a little bit about the actual standards. Now the ITU RBS 1770 standard, which is really what we needed, and thank God for it. Yes, it does have revisions and 1, 2, and 3, and each one has a different functionality that was added. 3 is the one that I tend to use because it has the gating function. I'll explain that later. Once we had the ITU standard set out for the loudness meters, we needed to actually have a scaling of some sort. So it makes sense to call it LUFS instead of dBFS. So we're now measuring loudness units full scale. To be honest, the true peak meter is far superior to the VU and the ppm. What qualifies a true peak meter? What is it that makes this a true peak meter and that not a true peak meter, even when I'm in ppm mode? A bunch of things. And the first thing is that this meter has an oversampling ratio of 4. That's the most basic requirement. And the oversampling true peak meter, when we're talking 4 times oversampling, is only accurate to around 0.7 dB. And for that, we needed this EBU R128 recommendation. And that basically sets our true peak level to not exceed -1 dBTP. Remember, when we're talking about true peak meters, we're measuring in dBTP, decibels to true peak. Let's talk about integration times, because that really is important. Then I'll quickly run through each meter and how to read it. I'm not going to calibrate anything until the next video. Otherwise, this video will end up being one of my famous epics. once we had the international standards all set out, they each defined different types of metering standards. So we had a type 1 and a type 2. So the type 2 meter had an integration time of between 5 to 10 milliseconds. Bear in mind that the VU has an integration time of around 300 milliseconds and a fall of around 300 milliseconds. So this has an integration time that is markedly different to this. Type 1 meter, strangely enough, which came later, improved the integration time on all these PPMs to around 4 milliseconds. The True Peak, because of its extremely fast integration times, will capture intersample peaks. I've explained this in another video and showed you how to control them. Most intersample peak problems are handled with just extra headroom. I've consistently maintained that intersample peaks are integral when you're mixing. Some people say, no, ignore them. The more headroom you have, you can stop worrying them. But that's nonsense. True peak meters have to consider intersample peaks. So what does that mean? If you're now counting more peaks and counting across shorter and longer integration times, you're going to have levels that are different to a PPM. In other words, a true peak, trust me on this, will be about 4 to 6 dBs higher reading than a PPM. Right, now let's look at the integration time. 300, as we saw here, yes, you can alter it, but as a VU, we tend to stay with around 300. This, let's say it's now at 4 milliseconds, but here's the problem. Whereas the rise is 4 milliseconds, the fall is 1.5 seconds. That's ludicrous. But there was a reason for that. At the time when it was developed, it was so that we could actually see the value sustained on the meter, so we could actually read it. If we had a shorter or a much shorter fall time, it would barely have time to register. So now we ended up with true peak meters. Right, these have to show true peak levels because any overloads in the digital system will cause aliasing distortions. In other words, as I said earlier, we have to calculate intersample peaks. And this thing does. Now, the typical 4 times oversampling true peak meter, which would be this, is only accurate to 0.7. We spoke about that. If we want to get more accurate, we need to extend the oversampling ratio. So if you want to have the most accurate, and I think if in Canada or the Canadian standard, they're down to 0.2. I'm not sure if that's 8 or 16 oversampling. But the problem you've got with higher oversampling ratios is that they really murder the CPU. So 4 is fine for what I need. Right, let's start. Let's start with the terminology. We have LKFS, LUFS, and LU. What do these terms mean? To be honest, they all mean the same damn thing. It's just the way we interpret them. Now, LKFS is an abbreviation of loudness K-weighted full scale. And 1 unit of LKFS is equal to 1 decibel. You're going to wonder why we got this LKFS if it's the same as LUFS. It's really because of the BS 1770 standard and the 80 SCA/85 standard. So we got the European and the international standards, ITU. They're going to vary by, I think, about 1 dB. So instead of -23, you'll get -24 LUFS. LU is slightly different because LKFS and LUFS are absolute measurements. And depending on which standard you use, loudness target could be 24 or 23 LUFS negative. To aim for a more traditional number, i.e. something that we don't have to worry about international or European standards, we can just work in LU. That's just loudness units. So now we can set our own target level without having to worry about these two varying standards. And to be honest, in audio production, that 1 dB is not going to make any difference. This is where confusion starts to appear in our industry. -23 LUFS, which you tend to see on a lot of these meters, is really for the broadcasting side of things. So the program loudness in the broadcasting industry is expected to be around minus 23 LUFS. But in radio, which is what we're interested in, it's around minus 15. So the loudness meter incorporates 3 parameters. What do these 3 different integration times mean? And why they're important? So this measures your entire program's perceived loudness. Whereas this deals with short term, which should be around 3 seconds. And then we have momentary, which I like to use, as well as short term, because it will show me all the intersample peaks that are happening within a few hundred milliseconds. LRA refers to the dynamic range, whereas on these kind of ppm and RMS meters, the middle section here, which is called the dynamic range, is represented by DR, whereas here, because we're now working in the true peak domain, it's called the LRA. Right, BS 1770-3. Why is that so important? Well, they introduced the gating function. And the gating function, particularly for mastering engineers and people working in film, is so damn important. I'll tell you why. Let's say you're running a whole song through in about 3 minutes, which is to actually play the whole audio through, press start, and it will calculate the perceived loudness or the average for me, and then I can set my target and work to that. But for us to be able to get the right reading, we need to have the right standards. I use the LUFS, which is the standard full-scale true peak system, against the EBU R128, which we spoke about earlier. And you can alter it here depending on what you want to work to, but I recommend you just leave it here. If you're working with the international broadcasting and you want to start changing things, you go ahead. You can see here we've got BS 17702/3. 3 introduced the gating function. Back to the concept of playing your entire audio through and having the meter calculate and display the information. Right. Why is the gating function important? Because when you reach quiet passages, you really don't want the meter having to calculate those quiet passages as well. It becomes too much, because then your overall program integration value will drop dramatically, because you're now including very low value amplitudes. So the gating function, anything that drops below a specified value, and I think minus 10 LU was the value, so anything that dropped below that was gated. Anything above that was left. So we had a far more accurate perceived volume average level across our mix. The loudness range, as we spoke about here, describes the overall program material range, and that includes the softest to the loudest bits. That's why the gating function is so important. To be honest, in terms of how these meters behave, that's all you need to know. Short-term integration, momentary integration, program integration. Those 3 are all that we care about. All these other values, for example, do we need max here on the momentary and the short-term? I do. Do I need true peak? Of course I do. That's why I bought the damn thing. But the way they all behave is slightly differently. LUFS works to target values. It's pretty much the same here, but you set your standards from here and work to that target, whereas the VUs, you can set your own. One thing I haven't mentioned here is the case scaling, which you will get on all of these, well, most of these meters. For example, I have them in Cubase here. These are the Bobcats, the American engineers scaling standards set, which just allows for headroom. So K minus 20 just says, okay, 0 now is actually at minus 20. It's the same as moving your fader down minus 20 dB and leaving there and calling that 0. Not very realistic, so we like to integrate and calibrate to that so that our fader stays at 0. Because I can pick the K scales here, I can also pick them here. I can create them in my VUs, By doing this, I've now set this to K minus 14. But we'll come on to that in the next video. Right now, what we've done is calibrate. Let's quickly run through how to read them. Because I'm running a sine wave and I've calibrated peak and RMS to read 0, I am getting a dynamic range of 0. My program value, because I've set it all to 0 and peaked at 0, is 0, which is showing here. And my short term, which is that 3-second window we were talking about, is also showing 0. So the sine wave is not very useful for us, but for calibration, it's exactly what we want. If we look here as well, on the BX meter, for example, peak is defined by the outer line, RMS by the inner line, and you can see that that's also set to 0 because we've calibrated to 0. This middle section is for dynamic range, and because we're not playing any audio that has any dynamic range, so to speak, you're not seeing that. So let's play the drum beat and look at all the meters and how they behave. Dynamic range is expressed here. Dynamic range is expressed there. Here I can see it on my meters, but what's the problem here? I'm not getting great accuracy, am I? A bit like this, a bit like that. All my activity is happening down here. Why? Because I'm still working off 0. Once I set my headroom, margin, be it the K standard, all of this will change. However, we can change the behavior of the needle. What I've done is I've introduced a second needle here by going to this section and having a longer hold time. That allows me to see what my last instance's peak or peak on the average value was. Wonderful. Let's say I want to now work with one of the standards here. Let's say I'm going K minus 14. What I've done now is allocate 0 as minus 14. Why not do it here? I'm on ppm. Let's go minus 14. Look how the meter behavior now changes. And it's slamming there. Why? Because we're overloading the bus. Beautifully expressed here. VU, let's give it that minus 14 headroom, as we did there. And look at our RMS value against our ppm or sample peak value. Considerably different because we're looking at averages. That's why I mix using averages, but I do like to keep an eye on what's happening on my peak values. It's the same here. Click, reference, integration, minus 14 there. Sorry, it says minus 16. They're a bit fiddly, these. Click on that, and there is our motion. Brilliant. I can have my hold time extended. My integration time I can change, but I don't like to do that. I'll tell you why, because I don't really see the point. Not for what I'm doing, not music production. If I, say, had a mad, crazy-ass drum and bass track and I needed to catch some of those intersample peaks, even if I drop this all the way down here, look at what I get. It's still not enough. I need this kind of information. It doesn't matter if I alter the full rate. I'll do it here as well. And have all this crazy stuff happening. It's great, yeah, but you try keeping your eye on that. This is why the ppms had a 1.5 second fall time. I prefer to have a slower fallback, and if I need to look at my intersamples, I check all this. Okay, first of all, legacy mode. Standard is the new look, legacy is the old TT dynamic range look. Outside, peak measurement also gives you a value reading here. RMS is there, dynamic range is there. So long as that's squashing in and out, wonderful. Filter is one of my favorite sections. Let me explain the 3 filters to you. A is a band pass, but it's boosted. C is the same band pass without the boost, so it's far more natural to how our ears behave. And K is something that I wouldn't use right now because it has a boost at 1 kilohertz and I think it has attenuation below 200 hertz. So you can either leave it on that if you want to use the filter, or leave it just on standard mode. Completely up to you. I prefer to go into this mode, solo my filters, and then work that section. But to be honest, I can do that beautifully in other meters. And I'll show you in the next video how. What else is left? Nothing. Everything else I will show you in the next video. How we calibrate and how we work to the loudness standards, how we select our LUFS and alter the settings. That's it. Thanks for your time.